Now we're going to look at how to use the limit definition to actually find the exact value of the slope at a particular point. Before we do that, I want to introduce you to the secant line. So going back to Desmos, we're going to turn off the tangent line and turn on the secant line. The secant line is, notice that it cuts through the curve, okay? So there's a point on either side of the curve. And let me just make a point about the tangent line that I forgot to mention in the last video. Notice when I do the tangent line at 2, 1 here, it does actually cut through the graph at another point, but when I'm talking about the point 2, 1, there's no point nearby that it also cuts through. So it's skimming the graph at the point 2, 1. So let me turn this off again. So here we have the red point, which is a point close to 2, 1, but not equal to 2, 1. And so this is a secant line. It cuts through 2 points with the kind of curve in between here. And if I were to move the red point closer to the black point, what I'm going to find out is that I get a line that's closer and closer to the actual tangent line. So I have here 2.05, 1.058. So that's going to give me something real. That slope's going to be really close. If I put the tangent line up there, you can see it's pretty close to the slope of the tangent line. Now, if I were to continue to move the red point until it actually equaled the black point, then I would no longer be able to find the tangent line because its slope would be undefined, because its slope is defined by subtracting the coordinates of the 2 points, okay? Subtracting the y values, subtracting the x values. If the points are the same, then their x and y values are the same, and I would be subtracting 1 minus 1 over 2 minus 2, which would give me 0 over 0, which is undefined. So I can't find the exact slope using the secant line, or can I? We'll find out. So let's estimate the slope using the secant line. So estimate the slope using a secant line. So what I need is another point very close to 2, 1. Let me write that so it's a little easier to read. Very close to 2, 1. So I'm going to say x equals 2.01. So f of 2.01, well, let me just start with writing what I already know. If I say x equals 2, then f of 2, it means I'm going to be substituting 2 into the function and finding y. And I just wanted to remind you if that's what f of 2 means. So 2 times 2 cubed minus 3 times 2 squared plus 2 plus 3. If you calculate that, you get 1. Okay, that's the y value. Now I want to make x equal 2.01, and I want to calculate f of 2.01. So that would be 2.01 cubed minus 3 times 2.01 squared plus 2.01 plus 3. Now what does that equal? Now on my calculator, I'm going to do this in a very efficient way. On the calculator, I'm going to substitute 2.01 for x. I'm going to just type in the equation, and this is what I get, 1.0103. So this equals 1.0103. To find the slope then, and this of course is the estimated slope, so I'm going to put the slope as approximately then, change in y, 1.0103 minus 1, over change in x, 2.01 minus 2, or 0.0103 divided by 0.01, which turns out to be 1.03 when you calculate it. So this makes sense. I said in the previous page that we drew a tangent line here and it looked like the slope was close to 1. So that makes sense. That is not the exact slope. That is just an estimate that is close to the slope using the secant line. But I still want to find the exact slope at 2, 1. So what I'm going to do here is, rather than using a specific value for the second point, I'm going to use a general value. I'm going to call this point x, f of x. And this point here, 2, f of 2. Now we know what f of 2 is. We know f of 2 equals 1. F of 2 equals 1 because we already calculated that up here. F of x would be the way I would calculate y for any value of x. But it's an unknown point. It doesn't have any specific value. But what I want to know is what happens to the slope as I slide f of x close to 2, 1, and closer and closer and closer. This can be written mathematically using a limit. We can say the slope is equal to the limit as x gets close to 2 of f of x minus f of 2 over x minus 2. So change in y, f of x minus f of 2 over change in x, x minus 2. And I want to know what happens as x gets closer and closer to 2. Well, you can see that if I substituted 2 in for x, I'm going to get 0 over 0. I'm going to have f of 2 minus f of 2 over 2 minus 2. Same point, subtracting the y's and the x, I'm going to get 0 over 0. So I need to be able to do some substituting here. So what I'm going to look at is this f of x is right here, is equal to this whole expression. So this whole expression is going to be substituted in for f of x. So I'm going to substitute. I think I'll do this on a second line just to give myself a little more room. So this is equal to the, maybe start over here, equal to the limit as x goes to 2, and I'm going to use red pen to show you what I'm substituting, x cubed minus 3x squared plus x plus 3, and then minus, okay, f of 2. Well, f of 2 I've already calculated. F of 2 equals 1. So this would be minus 1 all over, and then my unknown x value is x. My known x value is 2. That's what I'm trying to find, is where 0.21. So here are my known points, the 0.21. My y value, my x value. My unknown point is represented in red. If I substitute 2 in here, I get 8 minus 12 plus 2 plus 3 minus 1 over 2 minus 2. 8 plus 12 is negative 4. Negative 4 plus 5 is positive 1 minus 1 is 0. This ends up being 0 over 0, which I knew it would from this previous thing. This is 0 over 0 too. I can tell from up there that it's going to be 0 over 0. So I need to be able to find the limit. We have a way to find a limit of something like this when we get 0 over 0. I divide the numerator by the denominator. But first of all, I need to combine together the constants here. X plus 3 minus 1 is the same as x plus 2. So I'm going to rewrite this as the limit as x goes to 2 of x cubed minus 3x squared plus x plus 2 all over x minus 2. I know that there is a common factor in the numerator and the denominator of x minus 2 because I got 0 over 0. I want to find the other factor, so I'm going to divide using synthetic division. And when I divide, I will find the other factor. So 2 goes here, and remember I'm using my combined numerator where I've combined together the two constants. So I have 1, negative 3, 1, 2. 1. Quickly do my synthetic division here. Okay, 2 times 1, negative 2, 0. So remember this represents x squared minus 2x minus 1, remainder 0. So there's my remainder. So it divides evenly. So this is x squared minus 2x minus 1. I knew already that it would divide evenly. If it doesn't, then I've done something wrong. I can now eliminate my discontinuity, take the limit again. So the limit is going to be, I don't think I'll write this in. I now can substitute 2 in the remaining part here. This is going to be 2 squared minus 2 times 2 minus 1. Oh, sorry, I wrote something completely wrong just a second ago. This is not x squared minus 2x. It's x squared minus x minus 1. Some of you have probably been screaming half point at me for a little while, and you're very disappointed that you can't email me tonight and get a half point for this, because I just fixed it. Sorry. So this is going to be 2 squared minus 2 minus 1, which is 4 minus 2 minus 1, which is 1. Not a big surprise. We already knew that we estimated the slope to be very close to 1. we estimated the tangent line, the slope of the tangent line in the previous section to be very close to 1. So I know now that the slope at 2, 1 of f of x is 1. And if we want to put in the bird graph 1 meter per second, okay, so we can even think of that as velocity. And remember, this is also called the derivative. All right. Now, we can use this then to find the exact equation of the tangent line. I know that the slope of the tangent line is the slope that I just found. The slope of the tangent line equals 1 at the point 2, 1. So I have a point, I have a slope. I know the general equation of a line is y equals the slope times x plus the y-intercept. I can substitute the points for x and y, so 1 equals the slope, 1, times x, plus the y-intercept. Subtracting 2 from both sides, I get negative 1 equals the y-intercept. So y equals, slope is 1, so 1x minus 1. So here's the equation of the line. Now I'm going to check that it is the correct equation by graphing. And it should look like the line tangent to the graph at the point 2, 1. So if I graph this point, it's going to have some of it at point 0, negative 1. It's going to have the point 1, 0 on it. Those are a couple points I can plot. I can also use y-intercept as negative 1 and go over 1 and up 1 to find the slope. So I also know that it goes to the point 2, 1. So here is the graph of the tangent line. Okay, and so that looks very reasonable, it looks very accurate. Now, the last part of this, I'm going to ask you to try yourself, find the instantaneous rate of change at x equals 1. Try turning off the video, doing the problem yourself. Then you can turn it back on and I'll show you the answer and talk about it in just a minute. Before I do that, though, I just want to emphasize what I'm talking about here now is this point here, the point 1, 2. I want to find the slope at that point. So so at the value where x equals 1. Okay, if you got that the slope is negative 2, and this is your y, if this is your tangent line, then you did it fine and you're done. If you need to have it explained, then listen up. We say the slope is equal to the limit as x goes to 1 of f of x minus f of 1 over x minus 1. F of x is my unknown point. 1 f of 1 is my known point because I'm trying to find the value of the slope when x equals 1. So I substitute the equation of the line, which is the same equation that we were working with before. So if that was what was throwing you off, go ahead and stop and finish it. It is referring back to the same equation. 2 is the value when I substitute 1 in for x into this equation. And I already know that from the graph that I have the point 1, 2. So here are my two y values. Unknown y value minus known y value. Unknown x value minus known x value. When I substitute 1 into the function, I just get 2 minus 2 over 2. 1 minus 1 is 0 over 0. So I have to take it a step further. Combine together the two terms in the numerator. So I need to do 3 minus 2 here, which is 1. A little caveat here. In the previous problem, I ended up with a x plus 2 here and an x minus 2 in the denominator. Here I ended up with an x plus 1 and an x minus 1. That does not always happen. Okay, that is coincidence here because of the easy examples I picked. Please do not think that always happens. This constant in the numerator does not have to match in any way the constant in the denominator. Okay, once I have done this, I still know that this is going to give me 0 over 0. So I know that there's a common factor of x minus 1 in the numerator. I use synthetic division with my combined numerator that I just got here. 1, negative 3, 1, 1 are the coefficients. Divide by x minus 1, which means I put 1 in the box here. Here are my results with synthetic division, which means I have the other factor x squared minus 2x minus 1. When I eliminate the discontinuity, substitute 1 into what remains, I end up with negative 2 meters per second. Looking at the graph, negative 2 makes very good sense for the slope at 1, 2. If this is +1, this is -2, that makes good sense. Now, I know that the slope is -2. It goes to the point 1, 2. Using y equals mx plus b with this given slope and the xy values, I can find that the y-intercept is 4, and there's the equation of the line. So I'm going to graph this now to make sure that it looks reasonable. So it has a y-intercept of 4. I go over 1 and down 2. Over 1 and down 2. Or you can just plot a few points. I know that if I put in 0 for x, I would get 4 for y. If I put in 2 for x, I would get 0 for y. So those are both points. If I were to draw this line, then this looks very reasonable for the tangent line to the line at that point. This is actually a point of inflection of the graph, so it actually is slightly above the graph here and slightly below, but it still counts as a tangent line. It skims the graph right at that point, both above and below. Okay, so hopefully this makes sense. Your homework, the first problem will be very similar to this estimate graph, this estimating process. The second part will be like this, finding the limit. The third part will be finding the tangent line. So it goes step by step, just like the example. And if you look at the top of the second page, it'll give you all of the answers to the first page. Then the second page has some concept questions. So kind of go back and think about what we did on the first page, thinking about what the derivative means and estimating some things using the graph. Then the third page just gives you some additional practice on both of those types of things, the calculations and the concepts.